one of the consequences of all the theorems that we've done, and it's a nice fact using complex numbers, is that if you have a polynomial and one of the roots is a complex number, so it has a complex 0, then automatically one of the other roots is the conjugate. So this is really nice because it kind of reduces the stress of finding another factor. So if I have 2 plus I is a factor or a 0 of my complex number, then 2 minus I is automatically a root as well. So remember that conjugates negate your imaginary part. So if Z is a plus bi, then Z star or Z bar is a minus bi. So even if it's written as bi plus a, then your imaginary part becomes the negative, or you switch the sign. Let's go through an example. This is best described by an example. So let's say that I have f of x is equal to x cubed minus f of x is x cubed minus 5x squared plus 16x minus 30. And I tell you that 1 plus 3i is a root. And I tell you find the other roots, the other factors. Let's not use the word root. Let's say 1 plus 3i is a, you could use is a complex 0. Let's use the same wording as a complex 0. So there are two methods of solving this, either going through synthetic division or long division. Both methods would work, and because I'm only going through one example in this video, I will, or two, I'll try to brush through both methods. So using this rule, because 1 plus 3i is a complex root, then 1 minus 3i is also a complex root. And in this case, what you're going to do is just use those numbers. So you don't have to do what we've done before with x's, where we negate the x and so on. You just use the complex root as it is. What you can do is just first use synthetic division for this. So I do want to go through the synthetic division because it's good to practice them with complex numbers. So let's put the numbers in. We have 1, negative 5, 16, and negative 30. And what we're going to do is we're going to divide by 1 and then divide by the other, and then the last thing we're going to be left with is going to be the last factor we have. It's going to be a linear factor. So this is going back to one of our formal examples, that the lemmas is that polynomials can be written as in linear factors. So that's what we want to get to. So I want to use 1 plus 3i. So this is my first complex root. This is going to be 1 here. And this time you're going to multiply 1 by this whole expression. So 1 times 1 and 1 times 3i. So I'm going to have 1 plus 3i. And then you're going to add this. So I'm going to get, basically you're going to add just as you do with normal addition of complex numbers. So you're going to add the real part and then add the imaginary part. There is no imaginary part here, so you're going to leave it as is. Negative 5 plus 1 is going to give you negative 4, and then the 3i stays the same. Then you're going to have to multiply these two together, but you're going to have to do it on the side. So you actually have to multiply the complex numbers together, expand out. I'm just going to do this one, and then the others you can try on your own. Be careful with multiplying the i's together. So this is going to give me a negative 4 plus 3i minus 12i, and then 3i times 3i is 9i squared, which is a negative 9. So I get negative 13 and a minus 9i. So this is negative 13 minus 9i, and you again add these two together, and then the result you're going to multiply and so on. You're going to keep on going. I'm not going to go through the details of multiplying complex numbers. I'll give you the results. This is going to be 3 minus 9i, and again multiply these two together. You're going to get 30 here, which is going to give you a remainder of 0, which is what you needed. So you should get to this point. Now, once you have this, this is the quotient. This is what we have left. So I want to still divide by 1 minus 3i, so I'm going to use my results. But it doesn't look like what we've had before for synthetic division. But what you're going to do is just use the same numbers in the same order. So 1 minus 4 plus 3i, 3 minus 9i, because we're going to still do what we've done before, where we consider this as a constant, power of x increasing, and so on. And this is 1 minus 3i. Repeat the same thing. This is 1. We have 1 minus 3i, and I'll get negative 3 here, because the 3i plus negative 3i is going to cancel out. Minus 4 plus 1 is going to give me minus 3. Multiply these, it's going to give me negative 3 plus 9i, which obviously is going to cancel out to 0, which is what we needed. So what I'm left with is 1 minus 3. And remember, you take this as your constant, and then you increase the power by x. So this is just going to be x. So x minus 3. So this is a linear number. If it was a quadratic, then you can factorize the quadratic. It means that I have 1 minus 3i, 1 plus 3i, and x minus 3 as my factors. So the other 0 is x equals to 3. Sorry, this is not the factorization. Apologies if I've written the factorization as such. 1 plus 3 and 1 minus 3i are the zeros. So we always write x minus whatever 0 we have. So x minus 1 plus 3i, x minus 1 minus 3i, and then our last 0 is, I'm going to write it here, x minus 3. So our last factor, sorry. So the zeros are x minus 3, 1 plus 3i, and 1 minus 3i. So these are our zeros. And the factorization, then this is going to be the factorization is as such. So this is my f of x. So this is the full factorization. The other method is to actually start writing this up and expand it out. So if this is method number 2. I'm going to quickly go through it. So if I have x minus 1 minus 3i, x minus 1 minus 1 plus 3i, simplify it, expand out, and you should get a long expressions with i's and x's and squares and stuff, which will simplify to a quadratic without an I. So now that you have a quadratic, what you can do is take your f of x and divide it by this. Because when you divide it by this long expression, it should give you the other factor, which we got as x minus 3. So, because imagine you have, for example, 12 is equal to 2 times 2 times 3. So what you're doing is you're doing 12 divided by 2 times 2 in order to get this 3. So that's what we're trying to do. So you're going to use long division in this case. You're going to write your long expression here. So we have this, and then you're going to write your divisor in here. And you're going to complete the long division, and what you're going to get is the x minus 3 in here, so that is your third root. So that's an example to use of complex numbers.